In this video, we're going to do example 7.6.2. Let x and y have joint probability mass function p of xy, as given in the table down below. We're asked in A to find the marginal probability mass functions for x and y. And so we remember that the marginal functions are found by adding up each row and writing the answers in the margins, and adding up each column and entering the answers in the margins. And so if we add up the first row, well, we've got 1/16, 3/16, and 1/16. So add those all up and you get 5/16, and then we add across the next row and we're going to get 6/16, which we'll leave unreduced just so that we can see that everything adds up nicely to 1, and add the last row and we get 5/16 again. And so we've got, for x, we have the possible values of -1, 0, and 1, and the marginal piece of x is 5/16 and 6/16 and 5/16, and we can see if you add those up, 5 plus 6 is 11 plus 5 is 16. That does in fact add up to 1, so we are good. And we'll do the same thing, we'll add down the columns now, and so 1 plus 3 plus 1 gives me 5/16. 3 plus 0 plus 3 gives me 6/16, and again 5/16. So we end up by getting the identical distribution for y, since we've got those identical values of -1, 0, and 1 as possibilities for y, and so the marginal piece of y matches. So we've got 5/16 and 6/16 and 5/16. So that's part A. There are the marginal distributions of x and y. Now we're asked to show that x and y are dependent, which means that we need to find at least one value x and y so that the marginal is not, or the product of the marginals does not give the joint. So this is independence if the marginals multiply to give the joint. And so we need to show that there's at least one value where that doesn't happen. So let's look, I mean, any of them will actually probably do, but let's look at 0. So if we take x equals 0 and y equals 0, then we've got p of 0, 0. P of 0, 0 is here. That is equal to 0, which is not equal to, well, the marginal of x times the marginal of y, which is, so 6/16 times 6/16. That is clearly not 0, but that is what we get if we multiplied the marginal of x at 0 and the marginal of y at 0. So since we have one value where the marginals do not multiply to give the joint probability mass function, we can say therefore that x and y are dependent. Let's look then at part C. We're asked to show that x and y are uncorrelated. So we remember that the definition of uncorrelated means that we need to show that either the covariance or the correlation, it's obviously you need the covariance to calculate the correlation, so it's easier to do the covariance. The covariance is 0. So to calculate the covariance, we want to calculate E of x times y. E of x times y, and E of x times y is going to be over the sum over all x and all y. So that's the sum over all x and the sum over all y of xy times the joint function, p of xy. So if we go sort of in order, let's go through the table this way. We're going to get -1 times -1, so -1 times -1 times 1/16. And then we're going to get -1 x times y times p of xy. Well, y is 0. So we're going to get a 0 here. And then we're going to get 1 -1 times 1. So -1 times 1/16. So 1 times -1 times 1/16. And then plus x times all of these, right? We've got xy times this, so x is 0, so we're going to get 3 zeros across this row. So plus 0, plus 0, plus 0, plus, and then what do we have down here? 1 times -1 times 1/16. So 1 -1, 1/16, and then we get plus x times y, y is 0 again, so another 0, and then 1 times 1 times 1/16. And so what do we have here? This ends up by being a positive 1/16 and a negative 1, not 1/6, 1/16. And so those guys are going to cancel. And then what do I have here? Again, I'm forgetting all the 1s in 16. Okay, and I've got a negative 1/16 and a positive 1/16 here, and then so those guys are going to cancel. Everything else is 0. So E of xy is equal to 0. So we need E of x, and then we need E of y, right? Because the covariance is E of xy minus E of x times E of y. So let's calculate E of x. So the expected value of x is going to be the sum over all x of x times p of x, and so we'll use the marginal here to do that. So that is minus 1 times 5/16 plus 0 times 6/16 plus 1 times 5/16, and so that these two values cancel out for me again, and I get 0, and incidentally that's going to be the same value for y because y has an identical distribution. So that's E of y. So E of x is equal to E of y is equal to 0, and therefore the covariance of x and y, which is E of x times y minus E of x times E of y, is 0 minus 0, and therefore is 0. Therefore, that's exactly what we needed to say that x and y are uncorrelated. So take a look at exactly this. We have a situation where variables are uncorrelated, but they are not independent. So what we said at the end of the last video, you can have a situation if they are independent, they must be uncorrelated, but the reverse is not true. They can be uncorrelated and dependent. That is entirely possible. We've got two more parts of this. We're asked to calculate the variance of x and then to find the mistake in the following in the statement in E. So let's calculate the variance. E of x squared, so using the computational formula of the variance, E of x squared minus E of x all squared. Well, E of x we already have, not there. E of x we have here. We don't have E of x squared, so let's start by calculating that. E of x squared, which means I need to take the marginal and square the x value. So that is the sum over all x of x squared times p of x, which is going to give me, so the marginal value here, the marginal distribution, minus 1 squared is 1 times 5/16. So I'm going to get 5/16 plus 0 plus 1 times 5/16, right? That's what I have here, minus 1 squared. So 1 times 5/16, 0 times this, and 1 squared times 5/16, which gives me 10/16. So 10/16 is E of x squared, which is actually the same as 5/8. So we've got 5/8 minus 0, or the variance of x is 5/8. E says find the mistake. So we noticed up above that the marginals of y and the marginal of x are identically distributed, right? So y has the same distribution as x. Another way of saying that is x and y are identically distributed. Identically distributed. That's just a paraphrase of the same phrase there, since x and y, let's try that again, since y has the same distribution of x. So find the mistake here. If y has the same distribution of x, then covariance of xy, well, y is the same distribution as x, so that's the covariance of xx, which is equal to the variance of x. We've seen that relationship before. So that is clearly false because we just found up above that the covariance of xy is 0. And we just found in part D that the variance of x is equal to 5/8. And the 0, covariance, is clearly not equal to the variance. So what is the mistake? And the mistake is here. So the mistake happens exactly at this step. This is not true. If y is the same distribution as x, that's not the same thing. That's not the same thing as saying, y equals x. They can each take the same values with the same probabilities, but they're random variables. At any given time, x might be 1, but y doesn't necessarily have to be 1 at the same time. You could have x being 1 and y being 0, or x being -1 and y being 1, right? The probabilities attached are the same. They have the same distribution, but that does not mean that they are the same random variable, that there's a relationship of equality between them. And that's what you would need. That's what you would need to be able to make this assertion. So the mistake here is thinking that things are being identically distributed means the same thing as them being equal. It doesn't. In the next video, we'll go on to section 7.6.5, where we'll see some algebraic properties of the variance and the covariance.